Hi, today I'm going to design a low pass filter. First I'm going to start with pen and paper and explain how and why I'm looking for the parameters I am, and then I'm going to move on to some circuit analysis on my oscilloscope. To design a low pass filter, all you really need is a resistor and a capacitor. Here's the circuit that I'm using, and here's an equation that defines its gain. To make things easier for me, I just define the capacitor as a complex impedance. So ZC, ZR, ZC, ZR is for resistor. The complex impedance, that it's a form of resistance, but it depends on frequency. Therefore, it's not a static value like it is for, let's say, a resistor. So when I go from here to here, you can see that the impedance of a capacitor is 1 over SC, and the impedance of a resistor is just R. Since R is just a linear kind of device, if you can call it a device, it doesn't have any complex part. But in the capacitor, it does. It has an S. S is J omega. J is an imaginary number. In electrical engineering, we use J instead of I because I is already used for current. And omega is angular frequency. Angular frequency, it's not super intuitive as to what it means, but if you were to turn it into hertz, you can just say omega over 2 pi equals frequency in hertz. So after some algebra, I get this equation. This equation defines the gain of the system or of the circuit. And yeah, but that's not all too useful for me when I want to design this filter. Rather, I really want to know to what extent this filter works. And to know what extent, you need to know the cutoff frequency. So the cutoff frequency is defined as wherever the power of the system or the circuit is halved, or where the output drops by 3 dB. Don't really worry about what that means, but if you want to see the dB based off of the gain that I calculated earlier, you need to put it into this equation. 20 log and then magnitude of the gain equals -3. So I just set that as a -3 so that I can figure out what the cutoff frequency is. So then what I do is I put this 10 to the power of this, 10 to the power of -3 over 20, algebra, and then I get this inner part equals to 0.707. It might not be too intuitive, but 0.707 is 1 over square root of 2, and that helps out a lot when I calculate this. So then what I do is I take the gain equation from before, I use some algebra so that it's easier to calculate. So then I get 1 over RCS plus 1. The magnitude of this is going to be 1 over root this plus this squared. Actually, I need to put a squared there. So then how exactly, and then through some algebra, I have to figure out how to make this 1 over square root 2. That's just simply through algebra, you're able to say, if this is equal to 1, this whole thing is equal to 1, then I have 1 over square root 2. So then, therefore, omega has to equal 1 over RC. RC over RC equals 1. So then, this is where the cutoff frequency is an angular frequency, and then this is where the cutoff frequency is in hertz. So now, looking through it all, now I have the most important characteristic of a low-pass filter defined. Now if I move on to the oscilloscope, you'll see what this actually means. The equation I've found and some components that I have lying around my room. This is a cutoff frequency that I get. So using a 100,000 ohm resistor and a 1 nanofarad capacitor, I end up getting just about 1600 hertz as my cutoff frequency. Here's the circuit, resistor on the top, capacitor across, ground. Here's the input. And this is my analog discovery. This is what I use to analyze a network, for an oscilloscope, a power supply, and just about everything else that I need. And all of that is shown on my computer. So here I have a sine wave going through the circuit, sweeping from 50 hertz to 2 kilohertz in 5 seconds. And as you can see, the input is growing in frequency, so it gets smaller lengthwise, but the output, the blue one, also shrinks or attenuates as the frequency increases. Another thing that I didn't really mention on paper is that the phase is also changing. There's a phase delay involved on the output. So as frequency increases, the phase delay grows. So more and more the output goes this way, relatively speaking. But if I wanted to look at this as the frequency increases and I wanted to see the decibels, I go to my network analyzer. So I have the network analyzer set up to go from 50 hertz to 20 kilohertz. As you can see, the input, the orange signal, stays at 0. That's because it's 1-to-1. The input over the input is always going to be 1, so it stays the same. But the output, as frequency increases, it goes lower. So if I using the cutoff frequency that I found before, 1.592, one can assume that at 1.592, you'll find that it's negative 3 dB. Close enough. But you'll see that it's negative 3.2 something. That's because of the tolerances involved with the capacitor and the resistor. They're not going to be perfect, so they're always just a little bit off. So if I wanted to find the negative 3 dB point, it would be right around here at 1.4741 kilohertz. So at this very point, it's half the power of the input signal. Intuitively, that doesn't make a lot of sense. And right now, I'm going to show you what that sounds like when I put some audio through it. And finally, this is the circuit, the low-pass circuit that I designed. I changed the capacitor value from the 1 nanofarad that I had before to 1 microfarad, and then I changed the resistor to a variable resistor, but 10K potentiometer. So now if I play music through here, you'll notice that only the low frequencies get through. And when I turn the potentiometer, it changes the frequency response. That is to say, less or more frequencies get in. So the higher frequencies like voice or anything above treble don't really get through, but you could hear the bass all the way through. Alright, that's about it for this circuit. Thanks for watching.